Okay, so before we start, let me tell you a little story to kind of help you guys out with percent yield. Oh yes, we did talk about percent yield. First off, let me start off. Are there any questions? Do you guys have any questions? Because I'm just catching up on all of the messages.
I'm supposed to ask if you guys have any questions. Okay, he's back, guys.
Okay, so as I was saying, are there any questions? No questions? Okay, good. Okay, so we're going to talk about yield, right? And I think we talked about it before, but we're just going to touch on it again. So I did tell you guys my story about yield. Yes, no, maybe. Okay, so let me tell you my story about yield since you guys are not responding to me. So when I was in college, I was taking this class called analytical chemistry. Now, analytical chemistry is basically when you calculate, you use instrumentations to calculate how much of a reactant that you're getting. And so you do the calculations normally, right? And so you get what we call the ideal yield. So that the calculations that we do is called the ideal yield, okay? Now, what you get actually and what the instrument is going to give you is the actual yield, right? So I went through and I did this experiment and I did my calculations and everything like that. And then the yield that I got was, it was 82.3%. Now I'm still a first generation college student, never been to college before, never did anything quite like this before. Yeah, you remember the story? Okay, good. So you guys all heard this story, so I don't have to tell it. Okay, anyway, moral of the story is that in reality, you're never gonna get 100% yield, right? Because the chemicals that we're working with are typically, yeah. So you're never gonna get 100% yield. And because you're never gonna get 100% yield, that's usually due to a couple of things. One of the things is that the chemicals that you're typically using are not 100% pure. So there's always impurities that are going to be associated with it. And then sometimes what we do, we get side reactions. So there are other products that can be formed. And so depending on the type of reaction that you're getting, you may not get 100% of the product that you're looking to get. And then the last part is, of course, there's human error. We're always going to make mistakes. You drop a hair in there, you kind of spit a little bit when you talk, things like that could end up leading to you guys not getting 100% yield. Okay. Now, the way that we calculate percent yield is the actual over the ideal, or sometimes you'll hear it called as the actual over the theoretical. And then we multiply that by 100. Okay. So a solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. The barium sulfate precipitates. Do you guys know what precipitate means? Now, since there's no class here, you guys are going to have to respond, either, thumbs up or thumbs down or things like that. Or even speaking, it's okay.
Because it creates a solid or something to do with solid.
That's right. Yes, so precipitation is the creation of solids, okay? So let's start off with this very first equation. What is the first thing that we need to do?
Is it write down the equation?
That is correct. We need to write down the chemical equation, okay? So let's see. It says a solution containing barium chloride is added to a second solution containing excess sodium sulfate. Barium sulfate precipitates. So what is going to be my reactants? You guys can type in the window.
Barium chloride.
Barium chloride.
Plus sodium sulfate.
Barium chloride. And it's a solution, so that means it's what state?
Aqueous.
That's right. And the other one you said was sodium sulfate. What is the chemical formula for sodium sulfate?
Na2SO4.
Okay. Okay, so now what are my reactants? I mean, my products, sorry.
Barium sulfate and sodium chloride.
Okay, so we have barium sulfate. And sodium chloride.
Mm-hmm.
Okay, is that balanced? Oh, what are the states of these guys? The barium sulfate is going to be solid, liquid, gas, or aqueous. That's right, solid. And sodium chloride? Okay, so I'll give you the hint.
Solid too?
No. So
Aqueous?
what happens when you put salt in water?
It dissolves.
It dissolves. So what do you think is going to happen here, since that's salt?
Aqueous or liquid?
That's right. It's going to be aqueous because it's going to dissolve in the water. Okay. Is this balanced?
No.
No. What do we need to do to balance it?
Add twos.
Where?
Sodium chloride.
Okay. Okay. So now we have a balanced equation, right? 1Ba, 1Ba, 2 sodiums, 2 sodiums, 2 chlorides, 2 chlorides, 1 sulfate, 1 sulfate. Looks good? Brenda, it's just you and me, nobody else is there, so.
Okay.
Okay. I'm joking, there are other people there, but they're choosing not to talk or respond, so. Weird. It's my chat box. Okay, so. Now that we have a balanced chemical equation, we can actually use it to do stoichiometry, right? So we know that we're starting off with how much barium chloride?
3.18 grams.
3.18 grams. Okay. So, and that's barium chloride. Now we know, since we're using a chemical equation, and chemical equations are based upon quantity, right? It's not based upon mass. So how do I get it so that I can actually make use of my chemical equation? What do I need to do to my mass?
What? Honestly, I have no idea. Is it the moles?
That's right. It is the moles. So anytime that you're given mass, you have to convert it to moles. Okay.
Oh, okay.
So anytime that you're given mass, we have to convert it to moles, because the chemical equation is based upon quantity, and mole is quantity. Mass is just mass. Okay. So how do I change my grams into moles? What am I going to use?
I'm trying to remember. Is it the constant number?
No. There's this big old packet that you have.
Yeah.
Yeah, something in that packet, probably on that first page. Okay, let me pull up the periodic table. Maybe. That is really tiny. Okay, so if you take a look at it, we need to calculate its molar mass. Molar mass, moles, mass, molar mass.
Oh, okay.
So we have barium chloride. That's Ba. So looking at our periodic table here, how much does Ba weigh, and how many bariums do we have in barium chloride?
137.
Okay, so we have 1, and it's 137. $137.33. And then how many chlorides do we have in barium chloride?
2.
Okay, and chloride weighs
35.5.
okay. So then we multiply that times 2.
71.
Okay, so we add them together. So what is that? 208. And the units are grams per mole. Okay, so we can come down here. Let's go back to our page, since we used our periodic table for that. Okay, so we know that our molar mass is 208 grams per mole. Over here. Okay, so we could put the grams on the bottom to cancel out the grams. So we're going to put the 208 on the bottom. And we put 1 mole on top.
Yes.
Okay, now what is it that we actually want? I'm gonna move this out of the way so we can see the question.
Mhm.
What is it that we actually want? It says, the first one, it says, calculate the ideal yield. So the ideal yield is the part that we're actually calculating, right?
Mhm.
And it's the ideal yield of barium
Barium
sulfate.
sulfate.
Okay. So what is the mole to mole ratio? For every 1 mole of barium chloride, how many moles of barium sulfate do I have?
1.
1. So it's a 1-to-1 ratio.
Mhm.
So we want to get a barium chloride. So we'll have to put that on the bottom.
Mhm.
And so we want to get to barium sulfate. Okay, so I'm going to go ahead and erase this so it gives us a little more room. Okay, so now we have, if we look at our units and everything and look what cancels out.
Mhm.
So we've gotten rid of grams of barium chloride. We've gotten rid of moles of barium chloride. So we want mass. That's what we're looking for now because our actual yield is in mass. Okay,
Mhm.
so then how can I change moles into mass?
Do we find the molar mass for barium sulfate?
That is correct. We're going to find the molar mass of barium sulfate. Okay, so we have barium,
Mhm.
right? Okay, we have, how many bariums do we have?
1.
Okay, and then sulfates, how many sulfates do we have?
1.
And then how many oxygens?
4.
Okay, so we got 4 oxygens. Okay, so we know that barium weighed 137.
Mhm. 0.33.
And then sulfur weighs how much?
Sulfur. 32.06.
And then oxygen weighs about 16, right?
16, yeah.
And then we have 4 of them, times 4.
Mhm.
Okay, so we know 16 times 4 is what, 64?
Yes.
Okay.
$233.
$233 grams per mole. Okay, so here we're going to have moles on the bottom
Mhm.
because we're getting rid of moles, and that's 1 mole of barium sulfate. And then we're going to put our 233 grams on top. Now, is this looking kind of familiar with things that you guys done before?
Yeah.
Yeah. Okay. So let's go ahead and do that math. So we multiply across, so we have 3.18 times 233. Then we divide it by 2.
3.56.
What did you get? You got 3.56. Okay, so 3.56 grams of barium sulfate. Okay, so now we've calculated the ideal yield. So how can we calculate the percent yield? It
The
says-
actual
okay,
by the ideal.
okay, so we know it's the actual divided by the ideal. Times 100.
Mhm.
Okay, and what did you guys end up with?
94.6? 94.7, sorry.
Okay. 94.7%. Okay, so in other words, you pretty much recovered most of it, right? So it's pretty good experiment.
Mhm.
Okay, piece of cake, not too bad,
Yes.
as long as it's strawberry chocolate cake. Okay, so let's move forward. Everybody's good? Stephanie, are you good?
Yes, piece of cake.
Yes. You want a piece of cake? Yeah, I want one too. Yeah. Sorry. Okay, so let's go ahead and move forward. Everybody's good. We can move forward. Yeah. Okay. Okay, so the next thing that we're going to talk about is limiting reactants. Okay, so how many of you guys make cheese sandwiches?
Me?
Everybody knows what a cheese sandwich is.
Yeah.
Man, this is a rough crowd, man. Okay, so we got one person who knows what a cheese sandwich is. Everybody else don't. I know some of you guys are at work, so I get it. Okay, so let's talk about cheese sandwiches. Okay, so we're gonna make simple cheese sandwiches. Okay, so if we make a cheese sandwiches, how many slices of bread do we need?
2.
Okay, so we need 2 slices of bread. How many slices of cheese do we need?
1.
Yeah, because we're working on the budget. Okay, so we're gonna have 1 cheese. And then that's gonna equal 1 sandwich. Okay, so 2 slices of bread plus 1 cheese yields 1 sandwich. Okay, now let's say we're gonna have a party, right? And I'm really, I'm going all out for my guests. They're getting cheese sandwiches, right? So let's say I have a loaf of bread that has 20 slices of bread. And I have 8 slices of cheese. Based upon our equation here, our chemical equation here, how many cheese sandwiches can I make?
$10? No.
Are you sure?
16? No, sorry, 8.
8.
8. Okay. Why can I only make 8?
Because you only have 8 slices of cheese.
Because I only have 8 slices of cheese. That's correct. Because I only have 8 slices of cheese, I can only make eight cheese sandwiches, because our cheese sandwiches require 1 slice of cheese. Even though, if we looked at the bread, I have enough to make 20, right? I mean, not 20, 10. Okay. Does that make sense? So we can only make 8 cheese sandwiches because we're limited by the number of cheeses. Okay. Are you with me?
Yes.
Okay, good. Okay, so now we kind of understand that. So this is the concept of limiting reagents. And this is what happens a lot of times, where we'll actually start a reaction and one will be in what we call excess, meaning that we have extra. So what is an excess in the case of our cheese sandwiches here?
The bread?
the bread, okay? And then we know that the cheese was limiting, okay? And so the limiting reagent will dictate how much you can actually make, okay? So now that we've applied it to cooking, let's see if we can apply it to chemistry, which is exactly the same concept, right? Okay, so here we have 3 carbons and we have 2 oxygens, okay? So if we're making carbon dioxide, how many carbon dioxide molecules can we make? So our chemical reaction is 1 carbon, 1 oxygen molecule is going to yield 1 carbon dioxide. Okay, so how many carbon dioxides can we make?
Only one?
2?
We can make 2. That's right, we can make 2. It wouldn't be only 1 because we have 1, 2 carbons, right?
Mhm.
And actually,
Oh, okay, no, I see.
Yeah.
Yeah.
Okay, and we know that oxygen is O2, so we know we need those O2s to sit there and make CO2, right? So what is in excess then? Is the carbon in excess or
Yes.
the carbon is? That's right. So that means that the oxygen is what?
Limited?
Limited. That's right. So we know that the oxygen is our limiting reactant. Okay. Does that make sense?
Yes.
Okay, so let's do a problem then. Since that's a little too simple, let's put it up a notch. Calculate the mass of antimony 3 iodide, SbI3, that can be produced by the reaction of 129 grams of antimony, Sb, and 381 grams of iodide. Okay, so I'm going to show you guys the long way of doing it, okay, and it's the surefire way of doing it. And then if we have time, I'll show you the short way, okay? You guys ready?
Yes.
Yes.
Good. Okay, so first thing that we need to do is to do what?
The molar mass?
The what? Not the molar
Oh,
mass.
the equation?
The chemical equation. That's right. Okay, so it says, okay, so calculate the mass of antimony 3 iodide that can be produced by the reaction of 129 antimony and iodide. Okay, so what are my reactants?
Sb and iodine, I2.
Okay. That's right. Okay, they don't really tell us, but in this case, both of those are going to be solids, right?
No,
Yeah, iodine at room temperature is a solid,
okay.
but if you put it slightly above room temperature, it actually turns into a gas. Okay, so and then our product is going to be
the antimony 3 iodide.
okay. Which is also going to be a solid. Okay. What type of reaction is this, by the way?
Is it combination?
A combination, that is correct. Or a synthesis, that's right. Okay, is it balanced?
No.
No. Okay, so what do we need to do to balance it?
2 on the Sb, 3 on the iodine, and 2.
Okay, so that's a balanced chemical equation. Okay, so now the way that we would do it, since we see that both our reactants have values, right? As soon as you see this, the first thing that you should say is that this is a limiting reactant problems. So that basically means that we have to calculate how much we're producing for both of these, okay? So let's start off with the anthony. So we have 129 grams of anthony. Okay, so I want to change it to the number of moles. How do I do that?
The molar mass?
The molar mass. So what is the molar mass of anthony?
121.76.
We know that's grams per mole. Okay, so then that would get rid of grams of anthony. And what are we looking for, by the way?
The excess?
Yeah, we're looking for the SS, but it says in the beginning, it says calculate what?
Oh, the mass of the antimony 3 iodide.
Okay, so we need to calculate the mass of the antimony 3 iodide. So if I have moles of SB, can I use that to figure out how many moles of SBI I can make?
The ratio is 2:2?
That's right. So it's 2 to 2, right? So it's
1:1.
That's right. We could just say 1 to 1, or just to be safe, so we don't make silly mistakes, we'll just say 2 to 2 to keep it straight. Okay, so then moles are going to cancel out. And then
The molar mass for the SBI?
so we need the molar mass for SBI. So we know that SB, you said, was 121.76. And then I, we have how many of them?
3.
And that weighs
126.9.
So can we say 127?
Yes.
Keep it simple. Okay, times 3.
381. Oh, the total?
Yeah. Oops.
502.76.
502.76. Okay, so we have moles on the bottom, so we're going to put our moles on top already. So 1 mole on the bottom to cancel out those moles. And then we put 502.76 grams of antimony iodide, antimony 3 iodide. Okay. So if we go ahead and multiply across and then divide by the stuff on the bottom.
532.65.
Okay, so that would give us one case. And then the other case is if we started off with the iodide. So if we started off with the iodide, it's going to be 381 grams
Mhm.
of I2. And then what is the molar mass of I2? So we know that I is 127.
Times 2,
Yeah, so we have 127
254.
times 2. So that's going to be 254. For 1 mole of I2. Okay, so then grams are going to cancel out.
Mhm.
We're going to end up with moles. And we want to get, again, SBI3. So what is the mole ratio between the I and the SBI3?
3:2.
Okay, so we know for every 3 moles,
Mhm.
of I2, we have 2 moles of SBI3. Okay, so moles of I2 are going to cancel out.
Mhm.
Okay, so if we want the mass, it's going to do the same thing that we did over here, right?
Yes.
Okay, so we're going to go ahead and use that same number. Okay, so if we do that math,
$502.76. Is that right?
yep. Okay, so sig figs, how many sig figs should we have?
Two sig figs. Oh,
Three, sure.
sorry. 3.
3, yep. That's the same thing up here. We should have put our sig figs. So let's do that. Okay. So which one is going to be limiting? Which is going to give us the lower amount of product? If we started out with the I2 or if we started out with the anthony?
The I2.
The I2. So then the I2 is limiting, right?
Yes.
Because we'll run out of that first. Okay, so now we've talked about these laws and everything before. And there's a really important law that applies to all of this. Does anybody remember that law?
Is it the law of conservation of
The
mass?
law of conservation of mass, okay? So the law of conservation of mass says what?
Equal reactants, the mass of the reactants should be equal to the mass of the products.
Okay, so if we add the 2 mass of our reactants, so we have 129 plus 381, that's going to equal what?
510.
Okay, 510 grams, right? So we know that we've only are able to make 503 grams of anthony, I should be a 3 here, anthony 3 iodide. So if we subtract those two, that 510 minus that 503, That should give me how much of what? What is our excess?
The SP,
Okay, so we know that the SB, so we have 7 grams of SB, that would be excess. Okay. You guys are good?
yes.
Take a minute to digest it. Okay, while you guys take that minute and make sure you guys get everything written down, I need to go up to my. Okay, everybody got that down? Can you guys hear me?
Yes.
Okay, clear.
Yes.
Okay, so let's go ahead and move forward. Okay. So the next thing that we're going to talk about is solute and solvent. Okay, so the solute is what is being dissolved in the liquid, or often the way that we think of it is the one that is the lowest in quantity. So for instance, if we have whiskey and water, and we put a whole bunch of water and we put a little bit of whiskey in there, right? So the whiskey would be the solute, the water would be the solvent. Does that make sense?
Yes.
Okay. So how many of you guys have made Kool-Aid before? Anybody?
Not me.
I mean,
Yes.
agua de Jamaica.
Okay, so let's talk about mica. Okay, so when you make a mica, do you use the powder or do you use the flour?
I use a flour.
Okay, so even that. Okay, do you put a whole bunch of flour in there in the water, or do you just put a little bit of flour into your water?
More water, less flour.
More water. Okay, so which one would be the solvent?
The water,
The water. Which one would be the solute?
the flour.
Okay, perfect. Okay, and that's what the difference is. Okay, now when we put them together, they form a solution. So solute plus solvent is going to give us our solution. Okay, so if I have salt and water, which one is my salt? Or let's say I have a little bit of salt. Let's say I'm gargling with warm, salty water, right? A little bit of salt and a lot of warm water. Which one is going to be my solute? Which one is going to be my solvent?
Salt is the solute.
Okay. That's right. And the other one, water, is my solvent. Okay.
Mhm.
Pretty simple. And together, when we put them together, they're a solution. Okay. So this is just an example. So this here is, I believe this is copper, either copper chloride or copper sulfate, one or the other. And so it's going to be our solute, and then the water is going to be our solvent. So when we put it together, we have our solution. And we know that when we put them together, they dissociate. That's part of them being ionic compounds. Okay.
Mhm.
Okay. So I would ask, how many of you guys use the little water flavoring thingies, like the little squeeze bottles that you use to put flavor in your water? Anybody use those? Well, you guys are either all
Yeah.
natural.
Sparkling water.
What was that? You just drink
Sparkling water.
Okay. Okay. So this is a no-win situation, huh? So typically when we have something that is what we call concentrated, it means it has a lot of it in there. It's in large volume. How many of you guys cook?
I cook.
You cook?
Mhm.
Like when you cook, you use a chicken base,
Mhm.
like chicken,
Like a bouillon?
yes, like the bouillon, exactly.
Mhm.
Okay, so there's certain bouillons that are kind of like, they're kind of really thick and gooey, right? And you stick them in the refrigerator and stuff like that. And then you
Mhm.
put it in water, right? So by us putting them in water, we're diluting it, okay? Have you guys ever made juice or orange juice from concentrate? The little
Yes.
frozen things? Okay, so, okay, good. Okay, so that's an example of concentrate, okay? And then, so if we put that into a big thing of water, we're diluting it, okay?
Mhm.
So the term concentrate makes reference to it being a large quantity of what we're talking about, of our solute. And then when we dilute it, then we're diluting that solute. We're adding more solvent to, make it a little more dilute. Kind of like they do drinks at bars.
Yes, they water it down.
Exactly. Yeah. So here's an example of concentrate and dilute. So if you take a look at this example, we have a copper wire, copper wire, and then we have silver nitrate and a silver nitrate solution. Now, this first one is a dilute silver nitrate solution. So you don't get a lot of silver crystals forming on the copper wire. Where the second one is very, very concentrated silver, silver nitrate solution. So in this case, we're getting a lot of silver particles forming on the wire itself. And you'll notice the color change. The color is going to be bluer because we're getting a lot more formation of the copper 2 ion, where this one is really light blue because we're only having a little bit of the copper 2 ion. Okay. So when we're talking about solutions, we have to talk about concentrations. And there's a couple ways of us thinking about concentrations. And I'm going to tell you about the most common ones. There are other ways, but today I'm only going to tell you about the most common ones. One of them is called percent concentration by mass. And so when we do percent concentration by mass, it's going to be the mass of the solute divided by the mass of the solution times 100. Okay. So, and then if we kind of think about that, all it is the mass of the solute divided by the mass of the solute plus the mass of the solvent together, okay, times 100. Okay, and so then in this case, we're going to have a unit of percent. Okay, so when 125 grams of solution was evaporated to dryness, 42.3 grams of solute was recovered. What is the percent concentration of solution by mass?
Is it the 42.3 grams of solute divided by the mass of the solution?
Okay, so 43 divided by the mass of solution, which is 125 grams.
Times 100?
Times 100.
$33.8. 33.8.
You said 33.8.
Yes.
Okay. And we have 3 sig figs, right?
Mm-hmm.
Okay. Okay, so let's move forward. Let's see. Okay, so you're preparing a 2.50 times 10 to the second grams of a 7.00% by mass sodium carbonate solution. What mass in grams of sodium carbonate and what volume in milliliters of water do you use? Okay, and the important thing is that the density of water is 1.0 grams per mole. So I want you guys to try this problem, and then we'll come back and we'll talk about it. Okay, so you guys ready? Yeah. Sorry. Okay, so
Okay.
we know we have, in this case, we know the definition of percent by mass, right? So
Mhm.
it's the mass of our solute divided by our
Multiplied by.
solution, right?
Oh.
And then that's going to equal, or times 100. And that's going to give us our percent mass. Okay, so here we're given our percent mass. We're also given our solute. Okay, so you are to prepare a 2.5 times 10 to the second grams of a 7% mass. I guess that would be our solution, right?
Mhm.
Okay, and so they want to know the mass of the sodium carbonate and what volume. Okay, so then in this case, we should be able to, since we have our solution, we should be able to calculate our solute, right? Since
Yes.
both of these are given to us. So let's go ahead and plug those in. So we have, say, solute, and then 2.5 times 10 to the second grams times 100. And that's going to equal 7%. Is that everyone?
Yes.
Yeah, you can take a look. Was it, are they done? Okay. Okay. So let's go ahead and solve for solute. So we multiply both sides by 250. Change my colors here. Say 2.50 times. Okay. So then that's going to cancel out. And then do the same thing to this side. Okay.
17.5 to the power of times 10 to the power of 2.
Okay. So, and then we're going to divide both sides by 100. Okay. So what do we end up with?
17.5.
Oops. What was that?
17.5.
Okay, 17.5. Thank you. Okay, so now we know that our solute is 17.5 grams, right? And so they want to know the volume of water. How can we calculate that?
We have the density,
We have the density.
mass over volume.
Okay, so we know that the density is going to be mass over volume, but we also know that how can we calculate using our solution? So we know what is solution. What is solution made up of?
The water and the solid.
The water and the solute. So then in that case, we know that 250 grams minus 17.5 grams of our solute. And then the rest of it should be water, right? The difference should be water.
Yes. $232.5.
Okay. And so we know that to calculate the milliliters, it's what, 1 gram per milliliter. So then we could just go 2.35. Oh, sorry, 232.5 grams of water is going to be 1 gram per 1 milliliter of water. So it's just going to be the same thing in milliliters, right?
Mm-hmm.
Okay. Not too bad. Are there any questions? No questions?
No.
Okay.
No.
Okay, so let's move forward. Okay, so the next thing that we're going to talk about is molarity. Molarity is just going to be moles of solute divided by liters of solution. Okay. Now, this is the most commonly used form of concentration, particularly in the sciences. So we often will use it in bio labs and chem labs. And then sometimes you guys will see it on drugs that are being administered via nursing. Okay, so calculate the molarity of a solution made by dissolving 15 grams of sodium hydroxide in water and diluting it to 1.00 times 10 to the second milliliters. Okay, so what is the definition of molarity again? Molarity equals what?
Moles per liter.
It's moles of solute
Oh, yeah.
of liter solution. Okay. So how would I calculate the number of moles of sodium hydroxide? 15 grams. So how do I change from grams to moles?
Is it the molar mass?
That's right, it is the molar mass. Okay, so we know that sodium weighs, how many sodiums do we have in sodium hydroxide?
1.
Okay, so we have 1,
23.
the oxygen,
16.
the hydrogen.
1.
Okay, we add these together.
40.
40 grams per mole. Okay, so we have 40 grams of NaOH for 1 mole of NaOH. Okay. Okay, so we had 2 sig figs. This is 5 exactly. So what are we going to do with it?
Round off.
Do we round up or do we leave it?
We round up
Are you sure?
15 grams.
Because that's 5 exactly. There's nothing following it.
Oh,
So in this case, we would leave it. So it'd be 37 or 0.37. Okay. Our next question. Okay, so that would, oh, sorry, that's moles, right? So that would give us our moles. So if we have 100 milliliters, I'm going to put a little bar over it to let us know that that's the sig fig, right? So 3 sig figs here. So if I have 100 milliliters, how can I change that to liters?
Divide by 1,000.
Okay, so 1 liter is going to be 1,000 milliliters. So we get 0.100 liters. Okay, so then our molarity is just going to be 0.37 moles. So I'm going to use a capital M for molarity with the line underneath it. And we're going to divide that by 0.100. And so that's going to equal 3.7 molar concentration. Okay. Questions?
No.
Okay. Yep. Okay. So the number of moles, so molality is the number of moles of solute dissolved in 1 kilogram of solvent. Okay. So now molality is often used when we're talking about, it makes reference when we're talking about various properties, such as like boiling point and freezing point. And so it helps us kind of make some modification to things based upon the concentration of our solutions. Okay. And so you guys will probably get a chance to use it briefly, but very, very briefly. Okay. So how many grams of potassium chloride must be dissolved in 250.2.50 times 10 to the second grams of water to make 0.400 molal solution? So that little m is for molal. Okay. So what was the definition of molality?
Moles
And
of
I know
solute.
it's really close to molarity, but it's not the same. Molality. It's going to be equal to what?
The moles of solute dissolved in 1 kg of solvent. Small one.
of solute dissolved in kilograms of solvent, right?
Mhm.
Okay. So in this case, we're given our molality and we're given our water in grams. So what do I need to do to the water? Since that's going to be my
Change it to
solvent.
kilograms.
I need to change it to kilograms. Okay. So I have 250 grams. How do I change grams into kilograms?
Divide by 1,000.
You're going to divide it by 1,000. And so that's going to equal 0.250 kilograms. Okay. And so we can plug in and we can solve for the number of moles. So we can adjust our equation. So we get molal sorry.
Is it multiplied by the kg of solvent?
Molal times, yes, exactly. Molal times the kilograms of solute. I mean solvent.
Of solvent.
Yeah. Thank you. Okay, so moles of solute is going to be equal to molal times kilograms of solvent. So in this case, we have so it's 0.400 molal. And then we're going to multiply that times 0.25 grams or kilograms.
Zero 0.100. Sorry, 0.100.
Okay. Okay. Not too bad, right?
Piece of cake.
Piece of cake, chocolate and strawberry. Okay. Okay, let's see. Oh, we have to calculate our grams because we have moles, sorry. Because we're supposed to calculate grams. Okay, so then, oops. Sorry about that. I got carried away, got anxious. So we have 0.01 moles of KCl. Okay, so then how do I go from moles to grams?
Molar mass.
Molar mass. Okay, so what is we have how many potassium?
1.
Okay, and how many CLs?
1.
Okay, potassium weighs,
39.
and then Cl weighs
35.45.
So we add it together.
$74.
Okay, so we have 1 mole times 74.45 grams.
Let's see.
Okay, that's a potassium chloride. Okay,
Mhm.
okay, so let's keep going forward. Are you guys okay if I let you out a little early today? Oops, I got carried away. Okay, so,
Yes, please.
okay. So in terms of concentration, we have the percent by mass, we have molarity, we have molality, and there's normality. Now, normality isn't commonly used. It's typically used in really hardcore chem labs that are really ancient. So we're not going to talk about that this time. Okay. So we're going to move forward. Okay. So now when you're diluting concentrations, you're going to use this very simple concentrations to sit there and go from a concentrated to a diluted version. And it's I like to say, I'm going to change it a little bit than what's in the book. So it's M1 times V1, or sorry, we'll go C1 times V1 equals C2 times V2. Now, the way it works is that we're talking about concentration, and this is going to work for every type of concentrations, whether you're using molarity, whether you're using molality, whether you're using percentage, it's going to work all the time. Okay. The way that it typically works is that it's going to be your concentration times your volume. So your concentration 1 times your volume 2. Your concentration 2 times your volume 2. Okay. Now, this is going to be based upon the fact that regardless of how much you dilute it, you actually have the same number of molecules in there. Those number of molecules aren't going to change, okay? Or that quantity isn't going to change. So we always going to use C1 V1 equals C2 V2 to sit there and do dilutions, okay? Okay. So here, if we take a look at it, now the yellow balls represents the solute. Okay. Now the solute is going to be the same. It has the same quantity, 1, 2, 3, 4, 5. And then if we dilute it by adding more of the blue balls, we still have how many yellow balls?
5.
We still have 5. So in the sense, it's exactly the same quantity. The only thing that we're doing is changing the volume, right? By adding more blue balls. So. Okay, so the way that you would do this with the concentration, right? So okay. So the way that we would normally do this, so we have our concentrated version here, right? So we go ahead and we'll add our concentrated version, right? And then, so in this case, we're adding 100 mils of, in this case, this is going to be a 0.100 molar concentration. So we're going to go ahead and add 100 mils to that. And then we're going to bring our volume up to 1,000. So after we add our 100 mils to our 1,000 mil volumetric flask, we're going to bring this up to the 1,000 mark, right? And so we basically bring it up to that marking that is 1,000. I'm assuming it's about right here.
Mhm.
And so, and the thing about volumetric flasks, they're exact. I'll try to bring one to lab so you guys can kind of get a look at one. And so there's this nice little line to let you know exactly where they're at. And so this is how we typically make solutions in chemistry. We often use the volumetric flask because we can make it pretty quick. Now, if we did this, right? So this is our V1, this is our C1. And we know that V1, C1 equals V2, C2. C2. And then in the case, our V2 is going to be 1,000. So we can calculate the concentration of our C2. So just by solving for it. So we get V1, C1 over V2. And then that's going to give us our concentration 2. So in this case, we have 100 milliliters times 0.100 molar divided by 1,000 milliliters. So then our C2 is going to be equal to
0.01.
Okay. And again, this is the way that we typically do it in the lab. It's real quick. But the key is that, and this is the thing that a lot of students make a mistake of, you're adding this volume and then you bring it up to 1,000 volume, because that 1,000 is the solvent plus the solute, right? In this case, we're using a concentrated version of our solution to sit there and make the solute. Okay. So how many milliliters of a concentrated commercial hydrochloric acid, which is 11.6 molar, should be used to prepare a 5.5 liter of a 0.500 molar hydrochloric acid? Okay. So what was that equation that I just told you guys?
V1, C1 equals to
V1, C1 equals
V2C.
Okay. So we're trying to find milliliters. So is that concentration or is that volume?
Volume.
Okay. So we're going to say we're trying to solve it for, so that's our concentrated one. So that would be our V1. So we're looking to solve for V1. So we solve this equation for V1. So that's going to be V1 is equal to V2 C2 over C1. So then we just plug everything in, plug and chug at that point. So we have the volume of our C2, which is 5.5. Now this is liters. So we should probably change this since we want milliliters. So how can I change liters to milliliters?
You multiply by 1,000.
Okay, so this is liters. So we're going to go ahead and multiply that by 1,000. Okay, and the concentration was 0.5 molar.
Mhm.
Okay, and we're going to be dividing that by 11.6 molar. Okay, so this is going to cancel out. This is going to cancel out, and we should just be left with milliliters. So what do you guys get?
237.
Yep, 237 milliliters of HCl. Okay. Questions? Concerns? Cashola? Okay, good. Okay. So I think we're almost done. Hold on. Actually, we're going to save these last ones. We're going to stop here. This is a good stopping point. So we'll start on stoichiometry of solutions next.
Mhm.
Okay.
Okay.
Okay. So I'll see you guys on Thursday and Friday.
Good night.
Have a good night.